Okay, in this problem, we are using Lagrange multipliers to hopefully find the extreme values of f of xy equals y squared minus x squared. And the constraint is just the circle x squared plus y squared equals 1. So in other words, the x and y values, the only x and y values we're allowed to plug in are the ones that lie on this circle. Does that make sense? Okay. So the method of Lagrange multipliers tells us that del f is equal to, well, not exactly equal to del g, right? We can't say that, but they are parallel. They're vectors and they are parallel to each other at extreme values. So we're going to set up a system of equations that corresponds to the vector equation del f equals lambda del g. What the heck is g? Okay, technically g is x squared plus y squared minus 1 equals 0. G is the left side of that. But since 1 is a constant, if you forgot to set it equal to 0, it wouldn't affect anything here. Okay, what is del f? So so del f, let's write that down. Negative 2xi plus 2y j. Everybody believe that? And then what's just del g? So 2 space x, I'm going to leave a space there, xi plus 2 space yj. I'm leaving the space for the lambda because I'm going to multiply through by lambda. I don't know why, I just like doing that as a separate step. It's not necessary, you don't have to. I just feel like I'm less likely to make a mistake if I do that. And then you set, when vectors are equal, right? These guys are vectors. You set their corresponding components have to be equal. So we're going to set negative 2x equal to 2 lambda x, and we're going to set 2y equal to 2 lambda y. And along with the constraint equation, the original form of the constraint equation, those will be our system, that will represent our system of equations. So, all right, so we get negative 2x equals 2 lambda x. And 2y equals 2 lambda y, along with x squared plus y squared equals 1. There's your system. Now what you don't want to do, unless you know that unless you know x is not 0, don't divide the first equation through by x. Okay? You don't want to do that because x might be 0, right? You can't divide by 0. Now you have seen me do that, but that was only when we were in the situation where we assumed x was not 0, right? But there's no reason at this point to assume x is not 0. So maybe a better way to proceed would be to set this equation equal to 0 and factor. So I could say 2 lambda, I could actually add 2x to both sides and say 2x plus 2 lambda x is equal to 0. Would you buy that? Okay, I'm going to go sideways here just to save space. So what could I factor out of that? 2x, and then what's left? 1 plus lambda. And then that's equal to 0, right? So I think I'm going to try just making 2 cases from this one equation. I'm going to say assume x equals 0. That's case 1. Okay, so, well, 2x equals 0, but that's the same thing as saying x equals 0. Or lambda equals 1 plus lambda equals 0, which means lambda equals negative 1, right? So you could just think of this guy as case 1. Does that yellow show up? Yeah. This is case 1. This is case 2. Does that make sense? If x equals 0, what equation of your system just involves x's and y's? The last one. So we're going to use the last equation, x squared plus y squared equals 1. Plug in x equals 0, and we get y squared equals 1, right? Which means y could be plus or minus 1. So there's 2 critical values, or critical points here, right? 0 plus or minus 1. And that's it for case 1. Those are our critical values. I'm not going to I'm not going to put those in the function until the end. Okay? So let's look at case 2. When lambda equals -1, does anybody see an equation down here that would help me with lambda equaling -1? The second equation says 2y is equal to 2. I don't know why I'm still in red here. Let's see. The second equation says 2y is equal to 2 lambda y. And under this assumption, lambda is -1, so 2y equals -2y, right? Which means 4y equals 0, right? Which means y equals 0. So that means we're on the other end of it. And if we plug into the third equation, that means x would have to be ±1, wouldn't it? Just using the, when y was equal to, when x was equal to 0 as a guide. Since we have kind of the equation x squared plus y squared equals 1, the x squared and the y squared are symmetric. So then what do we get for our critical values? ±1 comma 0. Are there any other possibilities? Did I cover all the cases? So I think we're just going to make a table and plug in, right? So you could either make a 3-column table or just a 2-column table. Doesn't really matter. You could make a 2-column table and make the input, the left-hand column, the entire point if you want. And then f of x, y. Let's look at my function. Now, my function is this guy, right? Both y and x are squared, so do I have to worry about separating the plus or minus in either critical point? Nope. Because the negative is going to get squared out. So I get 0 plus or minus 1 plus or minus 1, 0. What happens when I plug in 0 for x and plus or minus 1 for y? I get 1 minus 0, right? 1 squared minus 0 squared. Or if you like, plus or minus 1 squared minus 0 squared. Plug it in right there. So I get 1, right? But what's going to happen when I plug in plus or minus 1? That should be a plus or minus 1 right there. Plus or minus 1, 0. So that's plus or minus 1 for x. So I get 0 squared minus plus or minus 1 squared, which is just minus 1, right? 0 minus 1 is -1. Now, I happen to know that there is going to be an absolute max and an absolute min simply because that circle is a closed curve and f of x, y is a continuous function, right? Remember the extreme value theorem? F is continuous. And your region is closed and bounded that f is defined on. That region that f is defined on is closed and bounded, f is continuous. Got to have extreme values on that region, right? But if you lose one of those conditions, the closedness or the boundedness or the continuity, then that whole theorem's out the window. It's not necessarily true. So what? Well, then the lower one has to be the minimum, right? -1 has to be the absolute min. +1 has to be the absolute max.